Welcome to This Explainer. Today, we're diving into the dramatic, high-stakes final stage of our fixed network series, the core network. If you've been following along, you know we've covered a ton of ground. But today, we're entering the absolute nerve center of operations. This is where raw hardware power meets incredibly complex routing software, and where the digital lifeline of an entire city or even a whole country is protected and managed. We're going to look closely at the massive data routers, the central authentication systems, and exactly what happens when the most critical links go down. Let's get right into it.
So far, we've tracked our data packets journey chronologically. We started at the customer desktop in Phase 1, moved through the street fiber drop cables in Phase 2, navigated the city aggregation switches in Phase 3, and now, Phase 4, the core, the ultimate destination. Just picture a massive Tier 4 data center with heavy security, endless optical fiber trays hanging from the ceiling, and giant chassis flashing with high-speed green and blue links. This is the absolute backbone of the entire country's internet. It handles massive data routing and connects our local infrastructure to the global underwater sea cables.
Okay, let's define our first major piece of heavy machinery in the data center, the AAA or brass server. As you probably know, AAA stands for Authentication, Authorization, and Accounting. Think of this as your centralized digital gatekeeper. Every single time a customer's home router boots up, before it can load a single web page, it absolutely must clear this gateway. The AAA server verifies the username, checks to see what billing speed package they're actually paying for, and finally assigns a valid IP address so the router can talk to the outside world. Without this software gatekeeper, all those physical fiber cables out in the street are completely useless. And this slide right here brilliantly illustrates the contrast in our core tools. On one side, you have the core routers. These are massive, high-capacity physical chassis using dynamic protocols like BGP and MPLS to route terabits of city traffic across oceans in literal milliseconds. They're the heavy lifters. But on the other side, you have the AAA servers. These are your centralized software gatekeepers managing every single local user authentication and billing IP assignment. So one handles the raw, overwhelming physics of moving global data, while the other manages the intricate, localized logic of user permissions. And for the network to function, both have to work in perfect harmony. So let's thrust ourselves straight into the action with our first crisis. What happens when this ultimate gateway to the global internet just fails? Picture this. Thousands of homes across multiple districts lose internet simultaneously. Boom, outage. Now, the physical street cables are perfectly fine. The street cabinets are flashing a healthy green, but the customers have absolutely no connection. This is exactly the kind of massive, spontaneous outage that creates instant panic in a network operations center.
Welcome to the blackout trap. What the customer actually sees is a solid red internet LED on their home router. But the root problem? That's miles away in the core. While their modem is throwing a PPOE authentication failure, your data center monitor is lighting up with a AAA server radius timeout. The physical network is perfectly healthy, but your central AAA database server has essentially frozen under heavy load, or maybe it's experiencing a database sync timeout. Because the gatekeeper is unconscious, nobody can get inside the network, even though the doors are wide open. All right, so here's your core fix. The absolute golden rule here: do not send technicians out to the streets. The physical layer is fine. Instead, you've got to use your operations dashboard. Step 1. Analyze your Radius server logs to confirm the signaling drops. Step 2 is absolutely crucial. You execute a manual failover command. This instantly forces all incoming login traffic away from the frozen primary server and reroutes it to the secondary active redundant AAA server cluster. Once the city is back online and that secondary cluster is safely handling the load, you move to Step 3. Clear the data cache on the primary server and run a software sync refresh before very cautiously putting it back into service. Well, that brings us to our second catastrophic scenario. Imagine you're sitting in the data center when, suddenly, support calls start flooding in with a very weird symptom. Customers are saying they can browse local web services effortlessly. Local streaming works, local news sites load instantly, but all international websites, global servers, and overseas games are totally, completely dead. What in the world is happening? This catastrophic symptom reveals a major backbone failure, which we call the global cut. When your dashboard flashes a critical alarm saying BGP peering session down with 100% packet drop, it usually means a submarine fiber cable buried deep out in the ocean connecting your country to a global internet data hub has just been physically cut. It could be a ship's anchor, maybe a seismic event, or actually could even be an accidental routing configuration mistake at the international border. Either way, your local network is fine, but your bridge to the rest of the planet has totally collapsed. Now, you can't exactly throw on a scuba suit and splice a fiber cable at the bottom of the ocean yourself, right? So to instantly fix this while specialized marine ships deploy for the physical repair, core engineers have to manipulate the digital network paths. First, you log into the core edge routers and check the BGP neighborhood status to confirm that the optical path is actually dead. Second, you manually change the BGP local preference or AS path configurations. By tweaking these numbers, you're essentially rewriting the digital map. Step 3. This tells the core router to completely ignore the broken oceanic link and instantly reroute all international traffic through an alternative secondary submarine pathway or maybe a terrestrial border link. You can literally restore global internet access in seconds, buying precious time for the physical repairs. All right, quick pop quiz before we wrap things up. Imagine you're on shift tonight in the core data center. The red lights flash. You encounter this exact massive failure where local traffic is up, but international traffic is entirely down. Based on what we just went over, what exact protocol or session must you inspect immediately on your dashboard? If you guessed the BGP peering session, you hit the nail on the head. As the foundational routing protocol of the global internet, Border Gateway Protocol controls exactly how our core routers talk to the other global internet data hubs. If that session goes down, the router simply doesn't know how to send a packet across the ocean, even if the user's home connection is completely flawless. Honestly, by mastering these fixes, you really prove your vital role in the data center. You ensure the AAA servers stay awake to let authenticated users in, and you expertly manage dynamic BGP paths to route around massive international cable cuts. You complete the data packet's ultimate journey from a simple desktop all the way out to the vast global internet. You're not just a technician anymore. At the core layer, you truly are the protector of the digital city. To wrap up this explainer, I want to leave you with one final kind of provocative thought about the massive stakes in the core network. Ask yourself, will your redundancy plan hold up when the next ocean cable snaps? Because out there in the real world, hardware fails, cables break, servers freeze. Your network survival doesn't depend on perfection. It depends entirely on how swiftly and smartly you can reroute around the chaos. Thank you so much for joining me for this analysis. Keep learning and stay sharp in the data center.